Hey guys, welcome back to the RCA RR-359 restoration project. Let me get you up to speed. When we left off, I'd been experimenting with a neon sign transformer and a filament transformer. We want to replace the original high voltage and filament transformer that was missing and had been replaced with a couple discrete transformers. One we think was from a TRK for the high voltage transformer, which was bad. They had cut up the chassis to mount it here. That's gone. They added a filament transformer down in this area. That's gone. We're going to make something that looks like the original and works like the original. So we're going to use this for the bigger high voltage rectifier tube, and we needed a filament winding for the lower high voltage rectifier that's used for the filament supply. So the idea was to take a neon sign transformer, which has the high voltage secondary, and add some windings around the primary to power the 2x2 tube, and we experimentally found that yes, it was possible. So I took some enameled wire, wrapped it around until I got the right number of turns to power a 2x2 at the right voltage current. Since then, once I determined that it would work, I secured it by with a little bit of Kapton tape, which is a type of tape that has good dielectric properties that can withstand a lot of voltage. I then painted on a couple layers of Corona dope for good measure, which is a type of lacquer that can also withstand a lot of high voltage. And then I put on some insulation on the leads. This is good for 5,000 volts. And I then covered it in hot glue. Might not be the prettiest thing, but it gets the job done. So we got our filament winding. We've got our tube filament winding. Sorry. We have our primary winding, we have our tube filament winding, we have our high voltage output, and we'll use this for the other one. We can put them on top of each other and fit it inside the enclosure. Alright, so let's move on. One of the rectifier tube sockets was damaged. I want to replace it. I've removed it. I'll give you a little forensics here on how it was made. It was riveted in place, and it was made up of 2 layers of phenolic with some discrete pins that were riveted to one of the phenolic layers, but not both. Not the greatest construction. These pins have a lot of force on them. This is pretty thin material, especially this layer, so it busted out. And several of the other sockets in this set are not in the greatest shape, so this one is more intact, but it's also got some damage on it. So I went ahead and I drilled out the rivets carefully. It was down in here. You can see there's a little bit of corrosion around there, but that's where it was mounted. They mount on the bottom side. This chassis steel is about twice the usual thickness, which presents a problem. So I'd hunted around for replacement sockets. I couldn't find anything quite like these guys. I haven't given up, but go onto eBay or the various tube vendors, guitar amp vendors and whatnot, you're going to find sockets that look like this, or more modern ones that are ceramic. But typically they all mount like this, either from below using this mounting bracket, like so, or from the top you can dispense with the mounting bracket and they've got this sort of twisty locking ring around there. Well, if you've got a hole, you put this on the top, you take this ring off, you put this on the top, and then you put the ring back on and it locks it in place. Well, if I go from below, well, here's the real problem here. This hole is smaller than these want, and the holes for the mounting ears are too close together. So if I was trying to mount it from below, one, this sticks proud and has kind of a beveled edge, and it just sort of rocks around. It doesn't fit in that hole right, and those mounting holes are too close together to work. So what I did do on this one is I took a file and I filed down these ears enough that I could get a screw through and mount it from below. That can work. This is kind of squirrely because it doesn't sit in that hole properly, and it's sloped, so it just kind of wants to rock around. And a pinch, it'll do. What looks cleaner is if you mount it from the top. So what I did do is I took one of them and filed it down a little bit, just enough that I can pop it in from the top. But because, again, that chassis is so thick, I can't install a locking ring around it. It just sort of sits there. And if you go to pull the tube out to replace it, the socket just comes out. But it looks real nice from the top, aside from these two holes. Now, in hindsight, if I knew if I was going to go the solution like this, I wouldn't have taken the rivets out. I would have just broken away the socket and left the original rivets in place. Yes, I can get new rivets. I can tap them in there. I can take care of that. But I don't have a good way of securing this socket. Yeah, if I had a lathe, I suppose I could make that slot wider or something. But what I'm going to do for now is either just mount this from the top and wire it in and just leave it kind of loose, with the hope I'm going to find a better socket at some point. Or I'll mount it from below. Either way, I'm not giving up on finding a better socket. And when he suggested, hey, you could have one fabricated. You could remove these original socket pins, drill out the rivets, transfer them to some new phenolic and all that. Yeah, I could. I don't know that I want to invest that much time and effort on a tube socket. I'd rather get this thing working in a reasonable amount of time. So, moving on. We'll figure out something with the socket. Moving on, high voltage caps. In this area, because when this transformer failed, it seemed to have oozed tar or wax, discolored this area. I really wanted to clean it, but the high voltage caps, filter caps, are mounted here and here, and they were kind of in the way. I'll tilt this chassis down in a bit and show you what I mean. But first, I want to show you what those caps look like. And here they are. The big guy is for the anode supply, 6,000 volts DC for the picture tube. There are two capacitors in here, both 0.03 microfarads, rated for, I imagine, 6,000 volts or better. I say I imagine because the label on both of these is gone. They were gone when I got them. These were also both corroded and covered in goo, which I think was wax that they had put on this to seal this. The construction on these, pretty sure they're oil-filled. Might be PCB containing oil. It was invented in the 30s, I do believe, so it's possible that that product existed when these were made. Either way, oil-filled caps tend to hold up pretty well over time. So these might still be good. That's another reason I'm doing this breadboarding of the power supply, is we can test these. Now we can test them with an LCR bridge to see at lower voltages what's the capacitance and what's the ESR, or check the leakage current. I can use my vintage cap bridge, which will put up to about 500 volts. But we want to test this at a good 6,000, 7,000 volts DC. So what we're going to do is when we get the power supply all breadboarded up, we're also going to connect this, and I'll do it with a resistor in series with this, so we can measure the voltage drop across the resistor, say 100K, 1 meg resistor, something like that. And we can see, we can measure the voltage drop across the resistor and do a little bit of Ohm's law. We can see what the leakage current is, if any. Now, conventional wisdom is, hey, you shouldn't use vintage caps, especially that, hey, this thing's rare, this is valuable. Yeah, so I'm kind of on the fence about that. I've heard from other collectors that these can still be good, but I also just got a comment, and I showed some photos of these, that this one went bad and took out the focus high voltage transformer on the side at the museum. I'm not sure what exactly he meant, if he meant the RR-359 at the early television museum in Ohio. Well, that's concerning, because of course I don't want to ruin mine. Now, if I did want to replace these, well, I could just put them back and not hook them up and install their high voltage caps down below, or I could open these up. These are made from steel that was, it looks like, soldered together. I don't know what kind of solder they used, if it's pure lead or lead tin or something else. But it sure looks like I could heat this up and pop the top. There's a big blob in the middle, so I'm guessing there's a lead or something, or maybe it's just to secure the cap, because as I said, I don't think any of the capacitor elements are attached to the can. So, yeah, we'll see. We'll see how it goes. We'll see how it goes with the testing. They cleaned up pretty well. I used some naval jelly, some evapo rust on them. This still has a bit of corrosion. Labels on both of them, as I say, are gone. If anybody out there who's watching this that has a 359, if your labels are intact, at least to some extent, have some information on them, I'd love to hear from you. I just barely make out, looks like a part number on this guy, but not really enough to read it. Just tantalizing traces of old labels. So that's what I know about these. Oh, and okay, so if I did want to restuff these, yeah, I could heat it up, potentially open it up, deal with whatever goo I find inside, thoroughly clean it out, mount modern film high voltage capacitors inside, and reseal it. Doesn't seem like it'd be all that difficult to do, other than the potential toxicity of what's inside. Alright, now let's take a look at the chassis from above. So here's where those capacitors mounted, and here's where that bad high voltage transformer was. So this is what I meant about the stuff. Some of it appears to be wax or tar. I was able to get it off with lacquer thinner. There was some corrosion. Used CLR on that. We still have some residue here I think I got to scrape off. Maybe that was from some charred wax or something. More down in here. I do not want to remove the remaining 5 boxes on here unless I had a really, really, really good reason to. That's the main power transformer. It's massive, very heavy, and these are the 2 main filter chokes, also rather large and heavy. That, I believe, is the high voltage transformer for the focus, and this is 2 filter chokes that are used in conjunction with these high voltage capacitors to form pi filters. So there are 2 high voltage chokes inside that. Now let's talk about that socket again. So here's what I mean about you pull the tube out, the socket just comes out. Here's what it looks like from above. Here's what that tube socket looks like before I put the tube in. I like the way that looks. No, it's not sunken like the original was. I like the way that looks. And once you install the tube, regardless of whether it's below or above, you don't really see the socket anyway, so I don't think I want to get too hung up on that. But if I do something like this, I most definitely do want to replace the missing rivets there. I'm sure there are modern brass rivets that look just like that I could install. I do have more cleaning to do over here. So terminal strip power distribution to the upper chassis, filament, and all kinds of various DC voltages. There's a bunch of taps on here going to all sorts of circuits in the set. And there's supposed to be a metal hood that goes over this and would attach to the screw. Mine's missing. I do want to clean this up a bit. Maybe just use a brass wire brush or something like that to clean up the metal a little bit. So we have a bit more work to do in here with cleaning with CLR and whatnot to make this look nice. As far as these boxes go, this is kind of the look I'm going for. This is about as clean as I want to get them. I don't want them to... I don't think they ever were polished, gleaming metal. This, I believe, was or still is cadmium plated in better or worse conditions in various areas. These, I think, if they were plated, it wasn't plated very well. Some of them look a little bit different shade of gray than others. But they're not painted, like the RCA painted a lot of these brown and other sets. I think it's just kind of raw metal. So I don't want to go crazy with there's a term, over restoration. I don't want to over restore these. I'm not going to get out a power polishing thing and then try to clean these up, especially when they're mounted in place like this. So this is about as good as I expect it to get. But I do want to clean up the chassis a little bit more. Now let's turn our attention back to the capacitors. I picked up this F&I RSI LCR meter, model 1020E, not too long ago. It's a nifty gadget. My favorite thing about it is this testing cable that comes with it. You can stick parts just into these slots to test them, or you can use this. Slides over, locks in, then you got these nice clips on the end. Now these things take some experience to know how to use them. For example, the test frequency. This one, some capacitance ECR meters, you don't have a choice. It's just whatever, 1 kilohertz, 100 kilohertz, are common values. But this, we can do 100 hertz, we can do 120 hertz, we can do 1 kilohertz, we can do 10 kilohertz, we can do 100 kilohertz. And they will all give you different readings depending on the type of capacitor you're measuring. Now this is used in a mains type power supply, not a switcher, not an RF type oscillator. So we'll go with 120 hertz, alright? And we are in capacitance mode. For the top parameter and second parameter, we can do the dielectric constant, we can check the quality factor, we can check the phase angle, let's check ESR. So as I say, I think the middle is the common, so let's go to either side of that and see what we get. Ooh, well, the 61 nanofarad, or 0.06 microfarad is good. It's supposed to be 0.05. Not crazy about the ESR that's jumping all over it. 220 ohms. I'm just curious if we change the frequency. So I go to 1 kilohertz, drops to 18. And capacitors and inductors are frequency-dependent components. And when you measure caps, so if we go to 10 kilohertz, now we're down to 3. Now we're down to 0.2 at 100 kilohertz. And if I go back to 100 hertz, now it's up to 320. So now that it means that it's bad, but it can be tricky to that was a dog upstairs. It can be tricky to know what frequency should we use. So I'm not worried too much about ESR right now, but it's good to see that the capacitance is very close to what it's supposed to be. I'll worry more about the leakage when we put this on a capacitor tester that puts a few hundred volts on it. Now let's check the big guy, which would be 2 sections of 0.03 microfarads. Again, I think that's the common. These aren't polarized, but just by habit I tend to put the negative on the common lead. Okay, that's also encouraging. Should be 0.03 microfarad or 30 nanofarad, and we're getting 33 nanofarads. Again, ESR is crazy high and jumping all over. And the other side, same thing. Let me grab a plastic film cap. I think I've got some 0.03s. Let's see how they check it. Yeah, here's a 0.033 6,000 volt cap. So if I was going to replace this with something, I would replace it with something like a couple of these guys. Rather have 8,000 or 10,000 volt caps, but this is what I have on hand. So let's see what this checks, or sorry, how this measures. So capacitance just about the same at right about 30 nanofarads. Oh, it came off. Boy, the ESR resistance on this is jumping over like crazy, which makes me feel better about the vintage one jumping all over. It's strange. I actually wonder, is that measuring, since it's an LCR meter, is it measuring resistance or is it measuring ESR? Ah, I think I was measuring ESR. Well, say, take some experience to know how to use these. You can measure XDQ phase and ESR. Okay, dielectric, Q, phase. Yeah, R is ESR. I also don't know how good this meter is, but it seems to me this value should not be jumping around like crazy like that. But, as I say, I'm focusing on the capacitance, and it's encouraging that these measure about the same. So I'll get out a vintage capacitance bridge now, and let's check leakage on it. Okay, here is my vintage solar capacitance bridge. Let's start with the big guy. Alrighty. So, leakage, 100 volts. No leakage. 200 volts, no leakage. 500, no leakage. If there was leakage, that would light up. Now let's start measuring the capacitance. Let's see, I'm on the C2 range. Yeah, right about 0.03. 0.035 or so. So that side looks good. I expect the other side will be similar. Yep, capacitance is just about identical. And leakage, no leakage. Alright, very encouraging. Now let's check the little guy. Well, this one does look a little oozier on that center terminal, like some of the oil inside might be leaking out. So again, let's check for leakage first. Ooh. So at about 500 volts, that is occasionally flickering. That light should never come on. How fast it flashes indicates how leaky it is. So I can't give you a microamps reading. But the fact that it came on at all, that's not good. We're not using this cap. Just for the heck of it, I'll try to measure the capacitance value. Now see, that measures fine. A little high. But then again, it was on the other one. Oh, sorry, it's supposed to be higher, that's right. About 0.06 on this one as well. But, yeah. So that also corroborates with that comment I got that, hey, in another one of these sets, I presume he's talking about a 359, that got leaky. So, it looks like we'll maybe have the fun of opening up one of these guys and seeing what's inside and cleaning it out and rebuilding it. Alright, I spent a bit of time going around the perimeter with solder wick, and then I spent a lot of time on this big blob that was in the middle, but I don't think I needed to, because while I was heating up that, the top started to come off. See, I thought that there was a slot cut in the top, and this tab was coming from inside and it was bent over, but no, I think it was just a flap on the top that they'd bent up, filled it with oil, and then bent down to seal it. So I think all I gotta do is heat this up a bit more. This corner here is the last place I was working on it. And then I think this will be ready to come off. Oop. Yes, there it goes. Alrighty. So, let's see about getting the insides out. Looks like we got a cardboard sealer there. Oh, it's going all around it. Okay. A bunch of paper towels here. Side. So what I want to know is, okay, yeah, sure, it's the usual paper cap and foil jelly roll inside, and then it's infused with oil. There's two caps in here, so there should be two sort of rolled up things. There we go. There's the two caps. Alright, all I want to know is, can I pull them out from this end, or do I have to do something with the lugs on the other end, which may not be so easy. If I get down in there, I can see a lot of the oil came out, so this is not filled anymore. After I broke that initial seal, a lot of the oil started leaking out, so I put a big wad of paper towels down and let it, the oil soak into it. So most of it is gone. Oh, yes. They are coming out. Fantastic. And there we go. There's one. And there's two. So, boy, I don't know how these were. There's no metal tabs coming out or anything. I don't know how these were connected to the lugs on the other end. Oh, now I do. That's an interesting system. I'll show you in a sec what I see. There are metal fingers. How well you guys can see that, but there are metal fingers running down inside here. These must have slid up inside those capacitor rolls. And must be secured to the lug on the other end, which may make it a bit challenging for me to restuff this. really hoping to avoid having to unsolder the other end, but I will if I have to. But right now I'm going to pause, and I'm going to clean this out thoroughly. Get rid of all this oil residue, clean off my needle nose pliers, etc. Alrighty, I cleaned it out thoroughly with some simple green and some commercial degreaser, and it is oil free now inside and out. And I really am going to have to undo the other end as well. I don't see how I'm going to be able to get in there and attach caps to these lugs without doing it. So here we go. Do the same thing on this end. And be a bit easier to do now since I don't have the cap inside and oil to deal with. Tempting to use a propane torch, but I don't want to roast these terminals. So I think that's some kind of plastic. Tedious, but I'll get it done. Alrighty, just about got it. So I'm gonna work on this end a little bit more. And there we go. Alrighty. Interesting. So I'm guessing these slotted parts were just coming right up into these. Oh yeah. See how the lead's twisted, so when I was trying to undo those nuts, I was twisting the leads around. Not the best thing to do, but well, we're going to rebuild all this anyway. So, looks like all we're going to do is clip these plates off. Tighten those lugs back down, and we attach our new caps down in here. Common middle, and 2 on the outside. So what am I going to use? Well, I need some 0.05 microfarad caps rated for, I think 2500 volts is a good safety margin. Output of the supply, I think, is around 1.5, 1.6 kilovolts DC. There may have just been an interesting development on rebuilding this focus capacitor. Got it all apart, got it cleaned up, and I was going to use 2 caps, something like this, inside. Which would work fine, I imagine. But I got a suggestion. As you may imagine, this project has drawn a little bit of attention on various forums, and I've been getting suggestions and advice from folks. One of them was about an interesting component from surplus sales in Nebraska, which so far has been my main source of goodies for this project, those Myconol sockets. So, took a gamble and placed an order with them. Plus I wanted to order up some more stuff anyway, so I got a bunch more of these high voltage CRT anodes now that I realize that, yeah, these are good quality. For I think they're $3 each. That's a deal. Also got a few other odds and ends, like some phono plugs. Yeah, believe it or not, I didn't have any of these. I need one for my Heathkit speaker substitution box. Also got a bunch of these high voltage caps. I don't remember exactly what the value is. About 0.056,000 volts. Hey, these look awfully familiar. Yeah, actually I already had a bunch of these. I didn't realize that, but these we'll use for electrostatic TVs in the future. Typically they use 0.005 for the vertical coupling caps. These are a little bit bigger than that, but they'll work fine, and these are cheaper than most of the options that are out there. But, this is what we really care about. So, Dr. Holden on the Antique Radio Forum suggested this cap, which is a thing of beauty to behold. Now, I looked at the high voltage caps on surplus sale in Nebraska a number of times, and I'd briefly seen these, and I dismissed it outright because the description of it is incorrect. They list it as a single high voltage capacitor. But he had one, and he showed me a photo, and he said, hey, the the part number matches mine, and mine is most definitely a dual. And he is correct, and it says dual right on there. It's not exactly cheap. I think this was 20 or 30 bucks or something like that. But boy, it's impressive. These type of caps, there's a few other varieties on Surplus Sale in Nebraska. There's a bunch on, not a bunch, but there's a few on eBay, ranging upwards of $100 a pop. These are made from reconstituted mica in some manner, military grade, really, really good stuff. So this is a dual 0.05 3,000 volt capacitor. Darn near identical to what this is. Now we don't have the label on this, but this is definitely a dual 0.05. I just don't know what the voltage rating was. But when I saw the dimensions of it, I was like, how many times on this project have you heard me say it's oh so close? So they listed the dimensions, and I was thinking, I don't think it's quite going to work. But I thought maybe if I angled it or something, I could make it work. But I don't think that's the case. I thought it was going to be too long, because I knew the length is right there at the limit. Now, one of the leads does go to the case, so that could be okay if we had a press right up against it. I could actually make use of that flap on the top where the oil seal was and run the lead out and actually solder it there. So that's actually a good thing on the top. That would, this is so close to being so perfect. And then on the bottom, where we have the two lugs coming out, we could connect it up. Now, I think on the original it's floating, but boy, I'll grab the schematic. I'm pretty sure the common lead just gets grounded. So that third lug would just be kind of redundant. I could be wrong about that. So it's these two guys. They go. Oh. I went back and looked at my order, and I can see why I thought this had a better chance of fitting, is that they listed the width of this as 1 3/4 inches. In other words, 1.75 inches. Okay, 1.75 inches. This is 1.8. It should fit, right? Yeah, but what is it actually? 1.83, 1.84. It's not 1 3/4 wide. So, oh well. Oh well, maybe manufacturing differences between samples. Maybe they didn't measure it super carefully. Oh well. This is what we got. I'm not going to buy a second one. I looked it up again. By the way, it was $35, so not exactly the cheapest cap. So will this fit diagonally? I played around with it a little bit, and yes, it can. But this outer covering, it's just sort of like Kevlar or something. It's adding just enough thickness. Also, I just realized there's a solder blob on the inside on that corner. But the opposite corner seemed clean. So, yeah, it will fit at an angle, but it's a little bit of a tight squeeze. It ends up kind of deforming the container a little bit. But yeah, it will just fit. And then this is turning into a parallelogram instead of a rectangle. But we can also see from the marks where the high spots are. The question is, can we safely scrape some of this away? After all, the internals are not going to be right at the edge, but we also don't want to go too far and ruin this thing. But perhaps, with a little bit of careful manipulation, scraping away of this, we can make it fit. Then the other issue is these contacts. So we have 3 of them. Now they sit pretty low. This also doesn't have a whole lot of clearance going this way. So these go to lugs. There's a hole drilled straight through these, and the leads of the cap need to go in there. There's 3 of them. And boy, it's almost tailor-made to fit right in there, but They're not quite dead center, so we need a little bit of clearance because we're going to have to bend these at a right angle and then bend them back up a little bit. And then there's the thickness of these themselves, which is going to take away that much from the interior. So the question is, if we do that, we need to leave a little space for lead manipulation. Will we still be able to close this? And then we have this lead, which needs to wrap all the way around and come out the other side. So yeah, I can bend this over pretty flush, but we're going to need a little bit of space at the top. So if we do that, and by the way, this has the highest potential on it. I'll show you the schematic in a minute. So we're going to need to put some insulation over that. It cannot come near this can. Going to need insulation that's good enough to about 2,000 volts. And then we're going to need some clearance on the other end to bend the leads and get into the lug on that. I mean, we're really, really pushing things. So what I could do, as I said, a moment ago, I think, is just make another box that's a little bit longer. And then at least I could retain these, and if I really went all out, just make a whole new box that's about 10% bigger. That would be no problem. But of course we want to retain originality, and I don't have to use this. I can use a couple caps like this and just forget the whole iron thing. So let's just put that on the back burner. Let's just wire this thing up on our breadboard with the cap out naked like this and see how it works. So let's get to the schematic. After all, the initial goal is to get this to work, then we can worry about perfection. Now, the original schematic, as written, I think is a little hard to follow what's actually happening, so I simplified it for you guys. So instead of showing the rectifier tubes with the filament and the cathode and the plate, I just drew them as if they were solid-state diodes. All right. And I forgot about ignoring the filament transformers. So what I'm showing here is, here's our AC power coming in, and pretend there's a power switch on here. We have two transformers. One of these is our 5,000 volt neon sign transformer. It's this guy. The other one is on the chassis. It's still the original. It's still good. And that puts out around 1,500 volts or so AC, or 1,000 volts, something like that. And that's for the focus voltage. And this is the most unusual part of this power supply, is conventionally you would have the focus control over here and just be a potentiometer between the low potential and the high potential, and the wiper would just go to the focus element on the CRT. But that means that you're going to have over 1,000 volts on the potentiometer, which is going to have a knob, and the user is going to manipulate it, while there's a shock potential there. And materials back then, well, it's not a high voltage potentiometer would not have been an off-the-shelf component. So rather than deal with all that and running high voltage wire up to the user control panel and then back down to the CRT, they vary the voltage going to the primary. So there's a 25 watt or 50 watt rheostat wired around a portion of the primary. Think of it sort of like a variac, but with a limited range, and that goes to the other side. So on the neon sign transformer, the higher high voltage transformer is just going straight to the primary. On this one side goes to the primary, the other side has this contraption here, which will vary the amount of power getting into it, which in turn will vary the power coming out of it. And then the rest of this is pretty straightforward. We have our rectifiers, and there's our dual filter cap, so this guy goes right there. So that these two are on the low side, and the common is going to the high voltage. So why do they do that? At first it seemed like, hey, why wouldn't you put the filter choke up here and have these both going to ground? But think about it. There's a filter choke. You've got a whole bunch of turns of wire in here in a big can. If it was on the other side, especially on this one, we'd have 6,000 volts on that choke, which would need high voltage leads going into the filter choke, and we'd have to heavily insulate the filter choke from the metal can that it's inside of and from the chassis and all that. But if we put it on the low potential side, we don't have to worry about that so much. So that's why they did that. And it works just as effectively. You could put, I've seen this before in other power supplies, you can put the filter choke on either side, and it accomplishes the same thing. So on our focus, we have around 1,200 volts out. Of course, it's going to vary with this control. And our other supply is about 6,000 volts. There's DC, of course. Now, another curious thing is that these don't go to ground. These actually go to B+. Took me a while to figure that out on the schematic, but I'm sure they had their reasons. I think part of it plays into the brightness control, the biasing on the CRT cathode and grid, that they don't want these at ground potential, whatever. There's a lot of unusual stuff in this power supply. When we get to the B+ side of things, you'll see there's a voltage divider with about 20 taps out of it with a crazy long string of divider resistors on that. So this is what we are going to breadboard up right now, with the exception of this for now, because this transformer is still on the main chassis. But I'm going to rig up the rectifier for this, and I'll put the filter cap, and likewise these filter chokes are on the main chassis. So we're going to do part of it. Eventually we're going to have our breadboard and the main power supply chassis up here, and I'll run extension leads over to it so we can get everything working in concert. But at first we're going to sub out a few things. So instead of these filter chokes, I'll just put some resistors in place of them. The resistance on these, I think they say, is around 13,000 ohms or so. DC resistance, so I can put a 15K, 12K resistor to simulate that filter choke being there. And we're going to wire up these rectifier tubes for real too. So that's what we're going to do right now.